Okay, hi everyone. So today we will be continuing our lecture on absorption. So basically what is absorption? I have explained in the previous lecture. So basically, whenever that we have produce an electromagnetic radiation onto your sample. So basically, it just will be absorbed or emitted. So it the characteristic of the wavelength that has been absorbed or emitted by your sample will depends on the identity of the compounds. Means that each compound would have a different characteristic, would have a different absorption or emission level. So this can be used, the difference can be used in terms of identifying the compound. Depends also on the amount of the analyte present in the light path, and also it will remains the same regardless of the quantity of the analyte present. Okay, so the wavelength that has been absorbed or emitted would have some interferences. So these interferences, we call it whether it's coming from spectral interferences, chemical interferences, or instrumental interferences. Okay, so for spectral interferences, it is the absorption or the emission of the other components in the matrix. So basically, when you have your sample, sometimes it is not only your compound of interest or your analyte inside the sample. So it will have some kind of other interferences or maybe other compounds that absorb at the same wavelength. So this absorption by these interferences compounds will we call as a spectral interferences. Okay, how about chemical interferences? It is the material determined that are not the same as the chemical or suitable form, right? And the last one is the instrumental interferences. Instrumental interferences is the excess illumination due to the imperfection in the instrumentation. So basically, maybe in terms of instrumental, it was supposed to light at 256 nanometer, but due to instrumental interferences, for some reason, maybe it is just shine at 300 nanometer. Okay, so from this slide, we want for you to know that what are the characteristics of the wavelength absorbed and emitted. So it depends on your sample, it depends on the amount, okay, and then what are kind of the what kind interferences that can occur inside your instrument. Okay, so basically for this for this slide, it is just showing in terms of uh, what are the wavelength that has been absorbed and what are the absorbed color and what are the transmitted color. Okay, this is not that important. Okay, so basically now we are going to look into the instrumentation in spectrometry. Okay, so basically this is the called this schematic diagram. Okay, so we call this a schematic diagram of any instrumentation. So any instrumentation means that whenever after this, when you are going to learn about UVVs or AES or AAS, or maybe in terms of chromatography as well. So when we say schematic diagram, it needs to be in this form. Means that you need to have a source, a monochromator, a sample, a detector, and must have a readout. Okay, so basically these are the schematic diagram that you should be able to know and do for every instruments that we are going to learn after this. Okay, so for example, in terms of UV visible, this is pertaining to UV visible instrumentation. So first of all, you would have your source, your light source here. Okay, so this is a part of the monochromator where they have an entrance slit a dispersion device and an exit slit, where this exit slit would only choose your wavelength of interest. And then this wavelength of interest, for example, in this case, you can see that only green green light that has been passing out through the exit slit. So that's why I say that this exit slit is function is to choose the right wavelength for your sample. You choose it yourself. Okay. All right. So the sample, this wavelength would be absorbed by your sample here, where uh, it can be absorbed or emitted or scattered. But in terms of UVVs, mainly it will be absorbed. Okay, so whatever that has been absorbed and transmitted, it will be detected by the detector. So basically, this is the form of your schematic diagram of any kind of instrumentation. So as I said, you need to be able to know on the schematic diagram of each of the instruments that you are going to learn. Okay, so the sample, as you can see that the sample here is being put inside like a glass cuvette. We call it a cuvette for UVVs, yeah? For UVVs, the sample will be in a cuvette. Cuvette ni means that like a box where it is a transparent box made out of glass or made up of perspex. Okay, all right. So yes. So when we look at the cuvette, it is called a sample cell as well. The common name is sample cell. So maybe we can call it cuvette for UVVs. So this cuvette has a very particular size. So for example, for this a standard 1 cm path. So this cuvette is 1 cm throughout lah, 1 cm wide, 1 cm length. Okay. So it just be like this lah. Okay. So 1 centimeter path. If you want to have a 5 millimeter path, also we do have 5 millimeter path, 1 millimeter path also we do have, and even we'll have 20 millimeter path. Okay. So all of these sample cells, the material that we are that made the sample cells, for example, for ultraviolet visible, usually the sample cells are going to be made by quartz. For visible, it is quartz or glass, but for infrared, usually it is sodium chloride or potassium bromide. Okay, so now we'll be continuing on the a little bit of explanation on the Beer's law. Okay, Beer's law is something that you'll be using in terms of measuring the absorbance value. Okay, so absorbance, the statements of Beer's law stated that absorbance changes exponentially as a function of linear change in transmittance. Okay, all right. So basically, absorbance is linear to concentration. So the higher the absorbance, the higher the concentration. The transmittance is exponentially dependent on the concentration. So all of this, we do have the Beer's law here, where it is okay. Transmittance is something that we do calculate from P and P0, means that this is the incident light from the light source, and then this is the pass-through light. Okay, so the P over PO, we got transmittance, the first one. Okay, so that's how we measure transmittance, means that the light that has passed through the sample and the light that has been beamed onto your sample, which is PO. Okay, so the difference, of course, there are going to be a difference because this incident, like in terms of analogy, for example, this PO might be 100%, but only 50% has been passed through. So where are the other 50%? It will be inside your sample where it has been absorbed or emitted or scattered. Okay, so P over PO, we got transmittance. So how about absorbance? Absorbance is the negative log of T. So when we do expand T, it is A log 10 PO over P. Okay, so the Beer's law stated that absorbance will be equal to molar absorptivity times path length times concentration. This is the Beer's law. Okay, so absorbance will need to be equal to molar absorptivity and then times path length, which is the size of the cuvette. So the size of the cuvette can vary. For example, when we do have 1 millimeter or 5 millimeter or 20 millimeter, it depends on the cuvette. And then C is the concentration of your sample. Okay, so this is Beer's law. So as I said, you need to know this Beer's law by heart. Okay, so it's very important. Okay, so this is the further explanation of Beer's law, Beer-Lambert law. So A equivalent to molar absorptivity times path length times concentration. And also you need to know in terms of unit as well, yeah? So unit is very important. So absorbance is unitless. Molar absorptivity must be in this liter per mole per centimeter units. B path length needs to be in centimeter and concentration needs to be in molarity, which is mole per liter or M, just a big M. Okay, this is molarity. You need to be able to make a difference between molarity and molality. So in this case, it is a molarity. Okay, so this is something that we have looked at before. Right. So basically, the higher the concentration, the higher the absorbance, the higher the path length, the higher the absorbance, and the higher the molar absorptivity, the higher the absorbance. Okay. So basically, this is also the explanation extension of the Beer's law. So this is something that we are going to correlate between Beer's law and your standard curve. Okay, there is a curve here. So for example, there is a curve here where the standard curve will be in y-mx plus b, and how it is correlate with an absorbance Beer-Lambert law. Okay, so for this one, I need to I need to give like a exercise, okay, on how are you going to use Beer-Lambert law and your straight line curve here. How are you going to connect between these two? You need to find out, okay? You need to find it out. Find it out and just jot down on a piece of paper that like whatever that we had done in lecture 2. Jot down on a piece of paper and then you just upload it in e-learning. Okay? On how are you going to correlate between Beer's-Lambert law and your straight line curve here. You need to know about these two slides, slide 37 and slide 38, so that you will be able to correlate between those two. Okay, just jot down on a piece of paper and then you just upload it inside e-learning. So this will be count as a attendance. Okay, let's move on to the next one. Okay, we have a lot of class activity, but I'm not going to do that. All right. So, this is the first one, the first instrument that we are going to learn, molecular spectroscopy or ultraviolet visible spectroscopy. Okay, so basically in terms of your, this is something that the idea of whatever that we are going to learn inside this chapter. Okay, you have a water sample containing methylene blue, which is a dye. So how would you know how much is methylene blue is in the water? So you have a sample containing methylene blue. So now you want to analyze it. You want to know how much is it. Okay. So UV visible region is quite large. Okay. So it spans out from 400 nanometer until 700 nanometer. So all of this region, 400 nanometer until 700 nanometer, is a visible, UV and visible region. Okay. So you need to know about this region so that whenever that you are doing an instrumentation, whenever that you are using UV-Vis instrument, you need to be able to set any kind of wavelength for your compound of interest. Okay, UV visible region. Sekejap, Okay. When a white light passes through or is reflected by a colored substance, a characteristic portion of the mixed wavelength is absorbed. Okay, this is not something that is important, but the remaining light will then assume that the complementary color of the wavelength is being absorbed. Okay, I'm not sure why is this here because this is not important. Okay, sorry. So this is not important, yeah, for slide 51. Okay, for slide 52, we are going to look at in terms of okay, what color appear at what kind of range. So for violet, which is at the lower end of the visible spectrum, would have some kind of at 400 and until 420 nanometer, and towards the other end, which is the red color, is it has been absorbed at 600 until 780 nanometer. Okay, so but I think that slide 51 and 52 you can have a read, but it's not that important for your understanding lah. Okay. Okay, so this is very important. So UV visible spectroscopy. So UV visible spectroscopy is used to obtain information about the atomic and molecular energy levels, the molecular geometry, the chemical bonds, and the interaction of the molecules related to the processes. So all of this information can be found by using UV-Vis spectroscopy. We also, so basically, we are going to identify the components of the sample, which is a qualitative analysis, identify qualitative, sorry, and then we are going to measure the amount, which is quantitative. Okay, so for UV visible spectroscopy, we are going to be able to do qualitative analysis and quantitative analysis. Okay, you still remember that I have talked about transition in the in a spectroscopy from okay, we have a electron transition, we have a vibrational transition, rotational transition. Kan? Alright, so for UV-Vis, this is a type of electronic transition. Okay, electronic transition. So what kind of transition that is able inside a UV visible spectroscopy? So all of the transition are here lah. So from sigma to sigma pi, sigma to sigma star. Sigma, so whenever there is no star, so for this one, pi or sigma with no star, all of these are at ground state. But For this one, it is at an excited state. Okay, so non-bonding is something that the atom that is not bonding to anything. Okay, so all of these are the types of transition that has been happen inside a UV visible spectroscopy. So you need to be able to know on the each of the transition. So what happens from N to pi star, pi to pi star, okay, N to pi star, pi to pi star, N to sigma star, pi to sigma star, sigma to pi star, sigma to sigma star. So we have 6 transition here. Okay. So all of these transition you need to be able to know on what does it mean. Okay. Right. So this is very important, yeah. Okay. But what makes a substance absorb UV visible radiation? So not all of the substance, if you put, for example, if you put oil inside UV vis, or maybe petrol inside UV vis, it will not be able to absorb UV visible. So what makes a substance that can absorb UV visible radiation? So what is the common characteristic here for all of these 3 compounds? First one, second one, and third one. What is the common characteristic? Okay, right. All right. So the common characteristic of all of these compounds, we can say that all of these compounds is a chromophore. Only a chromophore compound can absorb UV visible radiation. So what is chromophore? Chromophore, it is an unsaturated organic functional groups that can absorb UV visible radiation. So when we look at the definition of chromophore, it is said that unsaturated organic functional group. So when we look at the previous uh, compounds, these 3 compounds, all of these have unsaturated components here. So basically, all of this is the characteristics of a chromophore. You can see that there are so many unsaturated components inside the compound that can absorb UV visible. So as I mentioned earlier, for example, kalau you put petrol, petrol is just a hydrocarbon, okay, C6 or C8. So all of these hydrocarbon cannot be absorbing UV visible radiation, okay? All right. The presence of chromophore in the molecule is best documented by visible spectroscopy, but failure of most instruments to provide absorbance data for wavelength below than 200 makes the detection of isolated chromophores problematic. Okay. Conjugation is another part of a chromophore that can enhance the absorption value. Okay, so the molar absorptivities may be very large for strongly absorbing chromophores and very small for a weak absorption. All right, so the magnitude of molar absorptivity will reflect in the both of chromophore, the size of chromophore, and the probability that the light of the given wavelength will be absorbed when it strikes the chromophore. Okay, so for example, okay, for this one, I want to show you conjugation actually. All right, I will just jot down here lah. Okay, so this is one compound. Okay, this is one compound. Okay, which of these, with the first compound or the second compound, would absorb more in terms of the absorption value? That's where we look at conjugation. Conjugation means that the unsaturated organic functional group would need to be right after one another. So for example, for this one, the second one would have a much higher absorbance as compared for the first one. Because the first one, because the second one have a conjugated functional groups, okay, unsaturated functional group. Okay, so when it says conjugated, it it is right. Sorry, it is right one after another. Okay, for the first one, it is not right one after another. So basically, it is here the first one, and there is a space here, but it was supposed to be here, but it is here. So basically, it is not conjugated. Means that when it's not conjugated, it will have a much more lower absorbance value. Okay, right. So these are the example of chromophore. Okay, C double bond C, C triple bond C, C double bond O, N double bond O, and then even if we have a non-bonding electrons also for for in terms of halogen lah. Okay, all right. So these are the types of absorption types. Okay, in terms of absorption, when we looked at the tadi kan for the transition, we do have uh, sigma, pi, and n. So we have a sigma, sigma star, pi to pi star, n to sigma star, n to pi star, sigma to pi star, pi to sigma star. So we do have 2, 4, 6. 6 transition. So all of the transition depends on your compound of interest. Okay, for example, for organic compounds, saturated organic compounds containing heteroatom O and S halogens. So O and S halogens would contain a non-bonding electron. So straight away there is an N here, non-bonding. So all of the organic compounds would have a sigma and pi transition. But for a compound that contains a non-bonding electrons, it will have another N transition. Okay. For inorganic species pula, ions and complexes of elements in the first two transition series will be able to absorb bands of visible radiation in at least one of the oxidation state and colored. Absorption is filled and empty the d orbitals. So this is for inorganic species, right? So there is also another one which is change transfer absorption. So the absorption is by large complexes. Okay, so this absorption has a very large molar absorptivity, more than 10,000. So CTC consists of electron donor group and bonded to an electron transfer. All right. So in metal, for example, ferrum 3 complex with 110 phenanthroline, ferrum 3 with thiocyanate red color. These are the examples of a charge transfer absorption. So basically, all of these are metal ion complexes. So metal ion complexes will serves as an electron acceptor. This one. So basically, these are all the absorption types for UV visible radiation. It can come from organic compounds, it can come from inorganic compounds, and it also can come from charge transfer absorption. Okay, so but the most important thing is that you need to be able to decide on what kind of transition that is going to happen inside all of these absorption types. Okay, let me check something first. Okay, all right. So, UV absorbing compounds, as I said, that some natural organic compounds, we can see that all of these are chromophores and all of these are conjugated, especially when you look at beta carotene. This is the first one, second, third, fourth. All of this until the end is conjugated. Means that beta carotene would have a much more higher absorbance as compared to the non-conjugated chromophore. Okay, right. So, so basically, this is something that's for your reading only. So the nature of the shift and the descriptive term. So if there is shift of to a longer wavelength, we call it bathochromic. If it is a shorter wavelength, we call it hypsochromic. Okay. So this is your for your reading only. You can read it. Okay. So what is auxochrome? Okay, we have learned about chromophore. Now we are going to look at auxochrome. What is auxochrome actually? So auxochrome is a group of atoms that is attached to a chromophore which modifies the ability of the chromophore to absorb light. Okay, modifies the ability here. You need to be able to understand